All right, so thank you very much. Let me start by saying that this is joint work with Dimitris Korobilis, who acted as consultant for this project. He's at the University of Glasgow, a colleague, Bettina Landau, and Anthoulla Phella, who was doing a PhD traineeship at the ECB. Now she is at the University of Glasgow. I should also mention that the usual disclaimer applies. I forgot to write it down, but these are the views of the authors and not necessarily those of the ECB or the Eurosystem. So this work is about modeling inflation risks for Euro area data. And let me start with a short summary slide of the whole paper. Yeah? So just in case I run late, here is everything you need to know about the paper. Essentially, the question we address is which type of models and especially financial indicators, I'll tell you why in a minute, are particularly suited to forecast tail risks for inflation in the euro area, to these risks of inflation being too low or too high, as I will define in a minute. For this purpose, we adopt some models which have proven to be particularly useful in recent years, specifically quantile regressions, as well as for inflation, particularly, of course, Phillips curves models formulated within a quantile regression framework, and of course augmented with additional indicators, monetary and financial, to assess their usefulness compared to simple models, and also with and without, we explore several different specifications with time-varying parameters, and with and without stochastic volatility. So the data we consider is quarterly data from 1990 to 2019. When we started the project, it was before the pandemic, so for the paper we decided to end it in 2019 Q4. More recent data introduce additional complications, but for this paper we don't need to address them. We consider the HICP excluding energy and food because it's the more relatively less volatile indicator of inflation, so allows us to abstract from temporary influences of oil price and exchange rate fluctuations. And we consider, I would list later on, several financial variables to consider as predictors of tail risks of inflation. So the main findings, what we find is comparing several different specifications, several models with all different financial variables one at a time. We find that, first of all, from a, say, modeling perspective, quantile regression with time-varying parameters often dominate other specifications, other type of models, both in the short term, 1 year ahead, and the medium term, 3 years ahead. While as regards specific financial indicators, we find that specific credit and money volumes, as opposed to prices, often provide the largest, say, marginal contribution for predicting low and high inflation risks. So quickly, as regards to background, you probably all know the paper by Tobias Adrian, Nina Boyarchenko, and Domenico Giannone, AER 19. They, of course, they didn't introduce quantile regressions in the profession, but they kind of revived the interest, and also because they showed that a specific nonlinearity or asymmetry for U.S. real GDP was particularly useful to be exploited to predict risks of low growth, specifically showing that the risks of low growth in the U.S. are particularly sensitive to deteriorating financial conditions in the U.S., using specifically a financial conditions index, as well as the different components. This paper gave rise to a huge literature. Now every institution, every central bank, and many academic empirical macroeconomists also have started to explore this more systematically for different variables and geographical areas. And more recently also, has been applied to inflation. A notable paper was by David Lopez Salido and Francesca Loria at the Fed, who applied this whole infrastructure to assess, predict inflation risks, and they do it for both the US and the euro area, showing that they find that tight financial conditions carry substantial downside risks. Also here, they found this asymmetry, looking specifically, for example, the impact of credit spreads, also in the euro area from 99 onwards. In the background, when we started the project, also the ECB was carrying out its review of the monetary policy strategy, and in this context of the review of the ECB analytical framework, I was working specifically in the monetary analysis division, so we wanted to also explore more systematically what is the potential contribution of several money and credit indicators for the prediction of inflation and real GDP risk. Here I will present only the inflation risks, just to mention also why we have a lot of, among the financial indicators, a lot of money and credit volume indicators, among others. So the two main reference models we consider are the quantile regressions, which essentially is the one which Adrian and co-authors consider in their paper, plus also the Phillips curve model within a quantile regression form, augmented with financial indicators, which Lopez Salido and Loria considered and showed that provided some usefulness for the prediction of specifically low tail risk to inflation. Just to mention that, in general, the conditional inflation quantile equation, which is Q hat, you can see here, there is one for each quantile, so we consider 19 quantile. The lowest is the one associated with the 5th percentile of inflation, then the 10th, and so on, until the highest quantile is the one associated to the 95th percentile. And this is a function of a set of predictors as well as parameters, beta, which in our case, are allowed also to be time varying. We also consider stochastic volatility. And just to mention that also, among the predictors, we consider typically an intercept, lags of the variables, as well as one financial indicator of a time. In the extension, we are considering combination and multiple predictors, but at this moment we wanted to see which specific financial indicators provide the highest marginal, content or usefulness for predicting inflation tail risks. The inflation Phillips curve is very similar to Lopez Salido and Loria, and essentially it's a function of lags of inflation, which can be interpreted as intrinsic inflation persistence, long-term inflation expectations, some measures of slack. That's why also, by the way, for these variables we have to use quarterly data as opposed to monthly, but then some variations in relative prices, and then again one financial indicator at a time also here. As mentioned, so we consider the model of Adrian et al. And Lopez Salido and Loria. We also consider extensions with time varying parameters as well as stochastic volatility. Now, it turns out, I can already tell you now that while a lot of these models perform very well, especially with time-varying parameters, with stochastic volatility, they don't seem to provide an additional value added. In fact, the forecasting performance worsens. And our interpretation is that, indeed, of course, if you consider that there is one equation for each quantile, for which there are relatively few observations, say, I'll show you in a minute a chart for inflation, within each quantile set of information, you cannot expect typically, I guess, much volatility, or changing volatility. So at the end, adding stochastic volatility just adds an extra burden for the estimation, but without any really marginal value added. So at the end, we will present results without models with stochastic volatility and time-varying parameters in this context because of their, it turns out that they don't play an increasing prediction role. So all in all, we compare these models with several other specifications. Some are, of course, the baseline, very simple without predictors. By the way, everything we compare to is predictions of AR2 models. Then we also compare to not only quantile regressions, of course, with constant and time-varying parameters, also with mean regression models with stochastic volatility in this case. We also consider standard Phillips curves, which means standard without the additional financial predictors with constant parameters and time varying parameters. Some, also within a quantile regression framework. Some and some not. And then, of course, the last ones are the augmented with a financial indicator, different type of Phillips curve. So bottom line, this model number 8 would be more or less actually pretty much the Adrian et al. Model, while model 16 would be the Lopez-Salido and Loria. And we find that often the extension to time-varying parameters, 9 and 17, provide an increase in value added. Just to mention, maybe also within the basic models, the model number 3 is more or less very close to the Stock and Watson unobserved components stochastic volatility model, which is proving to be very useful to forecast inflation, except that we don't add the stochastic volatility formulation in the trend inflation, but it's pretty close to that. So all in all, we estimate for each horizon 160 models, because each of the ones augmented or so has one at a time 19 financial indicators. And out of these 160 models, I think only 8 have no predictor. The other ones have financial predictor added one at a time. So I won't spend too much time on this aspect. If my co-author Dimitris Korobilis were presenting, he would spend probably the whole one hour or more only talking about the Bayesian approach and the efficient Gibbs sampler and the priors and so on. I just mentioned that compared to previous approaches, this is not the first time we estimate the quantile regression models with time-varying parameters. We have a flexible Bayesian approach, as opposed to previous, mostly we're concentrating on non-parametric approaches. We derive an efficient Gibbs sampler, which Dimitris also, I think, expanded in a parallel companion paper. Horseshoe prior has some advantages, and we are careful also in ensuring non-crossing of quantiles, which is often a problem in this type of models. Forecasting, well, we consider 19 quantiles, and then we concentrate for the lower, so for prediction of low tail risks, or like left-hand side tail risks, or low inflation, the quantile associated to the 5th percentile, and for high inflation risks, the 95th percentile. We look at different horizons here. We report data for the first and the 1 year ahead for short term and 3 years ahead for medium term, more or less. There is no major changes if you consider also 2 years or 1 quarter and so on. In terms of assessment criteria, we look at both quantile scores, which are typically used in this literature since the proposal Giacomini and co-author. The advantage of this is that it's a metric for forecasting, say, average forecasting error, but it is specific to each quantile. So we will see that different models are selected for the higher and lower quantile. And also in parallel, we look at the prediction likelihood for an overall assessment of the whole density in forecasting. This is the series we want to forecast. In terms, you can see that in terms of from 1990 onwards, just to mention that, core, what sometimes is called core inflation, never really went negative. So the lowest quantile is associated on average with 0.7 more or less inflation. So the low inflation risks in this model are not really deflation risks, while upside inflation risks, are something which has not been seen for all of the 90s, but more recently they have been. And so in a way it is, suggesting that this, the whole free infrastructure and exercise is becoming particularly useful also in the current environment. Just to very quickly show you which financial indicators we consider. As mentioned, there are both narrow and broad money, different type of credit volumes, loans to non-financial corporations, loans to households, the sum of the two, and total credit, which also includes corporate bonds issued by non-financial corporations. We look at this both in terms of growth rates and in ratios to GDP. And then we consider also other obvious financial indicators, including asset prices, stock prices growth, house price growth. The KISS indicator, the composite indicator of systemic stress, which has been proven useful, especially for GDP. So we are considering that as well. Corporate bond spreads, slope of the yield curve, and two lending rate spreads, which are associated to some of these credit variables. So we consider both financial variables and financial prices. And let me show you the results. So we do a forecast competition out of sample. both for, and here we show the results for 1 year ahead. The next slide is for 3 years ahead. And we look specifically at measures of, as mentioned, low inflation risk, high inflation risk, and the overall density. Let me concentrate on the two-tail risks, and we show the three best ranking models among these 160 models we estimate for forecasting. And what we see is, first of all, let me see also the rankings based on the score, which is the ratio of the quantile score of this model compared to the AR2. If it's lower than 1 for the two-tail risks, means that the forecasting performance is better than the AR2 model, and the lower it is, the better. Overall, we see that often models with time-varying parameters are among the best performing ones, sometimes within a quantile regression or sometimes not, but and also typically with financial indicators, which for low-tail risks is, includes loans to private sectors and 1 to GDP. But you can see that especially the largest gains are for prediction of high inflation risks, especially for loans to firms and loans to private sectors. Not very much of a difference, so we typically look at quantile regressions with time-varying parameters as a reference models. For 3 years ahead, we have similar results. The advantages or the gains for prediction of low inflation risks are even lower, but are there. But for high inflation are particularly strong for 3 years ahead horizon. Again, with slightly different indicators. Loans to households is particularly good, as well as private sector loans to GDP growth, quantile regression without time-varying parameters. But in this case, for the best is in this for a quantile Phillips curve. We wanted to understand also the good performance of this type of model. Is it due to the time-varying parameter specification more, or to the contribution of the financial indicator? So here we compare the best, say, for 1 year ahead model, which we found in terms of a time-varying parameter quantile regression model, specification with and without the financial indicator. So this would be, this column would be this with and with and without the two lines for the low inflation risk and for the high inflation risk. And this is with or without, with fixed parameters versus time-varying parameters. And we compare the evolution of the quantile score for the two models. And you can see that most often in both cases, the model without either the financial indicator or with constant parameters would make strong prediction errors in specific periods, which could be sometimes concentrated around the Great Recession, but sometimes also in other periods. So suggesting that both the contribution of financial indicator and time-varying parameters appears to allow us to avoid these big forecasting errors. And this is the same story for 3 years ahead, essentially, for both, here is the loans to the private sector to GDP ratio and the loans to household for the higher inflation risk. And sometimes it's not only spikes in specific periods, but also prolonged forecast errors, which we managed to avoid. Just to mention that in terms of follow-up work, we are doing something similar for GDP and applying a comparison to the US and Euro area. And what different referees suggested is also, to instead of using one financial indicator at a time, since we developed this framework which allows for a high dimensionality estimation, put several different combinations of whatever financial indicators, be it one principal component for each category, or anyway multiple ones to see a little bit what is really, what can be defined as the optimal model for forecasting inflation. So, more or less, I'm done. I have some background slides in case anybody wants some more details, but otherwise.
Thank you very much, Sigal, for inviting me to discuss this exciting paper. So let me start with a few slides to motivate why the work that Alberto Musso presented is relevant. Well, you can think of inflation nowadays as being a silent killer, okay? It kills our purchasing power, is killing our saving. And we all care about this. In fact, like, you know, if you go on Google Trends and then you search for how many people have been searching for inflation, as you can see, there's been a spike in recent months compared to, you know, the historical average. So we all care about inflation. And I've stolen this slide from the presentation that Gita Gobinath gave a couple of days ago at the Jackson Hole. But, you know, the problem is that we don't have the right models. You know, our current models fail to predict, you know, inflation. So it's important to come up with, you know, better model, you know, and more sophisticated model. And this is exactly what, you know, the authors of this paper are doing. Let me give you a quick summary. Alberto did a great job, like, describing his result. And so what does this paper do? Well, the authors propose a new econometric framework to model and forecast inflation risk. So there is a methodological contribution because they implement a quantile regression with the time-varying parameter, and then they've developed a new Gibbs sampling algorithm, you know, for the estimation. And what do we learn? Well, we learn that this new methodology actually help us improve the prediction of the core inflation the risk for the euro area, you know, relative, say, to a traditional benchmark, whereby you can use like a simple regression with time-varying parameters. And then they also use a number of predictors, more than 20 predictors, and they show that, you know, among them, you know, loans to the private sector, loans to firms, so on and so forth, can actually improve our forecast of the future inflation risk. So my first reaction was, that's a great paper. You know, we can learn a lot from this application. However, I was invited to discuss the paper, so I had to have, you know, I have to say something. And then I thought, well, you know, let me think whether, like, you know, we can improve the paper. Of course, like, my comments are very marginal. I would say my 2 cents worth comments, because I'm sure that they won't change the big picture of the paper. Now, my first comment. My first comment is, well, you know, as the figure summarizes, is that, well, you know, you try to be comprehensive, but, you know, you squeeze together so many different combinations, and then there is little economic explanation. You know, there is not much narrative, so the paper reads very much as a heavy econometric paper, and I would expect from, you know, people working for the ECB to add a little bit of economic narrative to the paper. I'm familiar with Bayesian methods, so I wasn't scared. I might imagine that, like, you know, an average reader might basically just skip most of the paper. So, you know, I would really encourage you, like, to add more economic insight, you know, to better position and broaden up the audience of people that eventually might read this paper. Okay? So this is not a criticism; it's just an encouragement to you know, to make your paper broader. Then my second comment is about the state space. So you have pi, which depends on a set of parameters. Your beta will vary depending on the quantile, and the beta is time varying. But then the beta follows a random walk, and then I ask myself, okay, how can I use this setting for predictability? Because if I want to predict future inflation, I cannot assume that beta is a random walk. I know that it makes your life easier when you do the estimation, but if your task, your main goal is to predict, you know, future inflation, especially if you look at the left tail, well, perhaps you need to be slightly more sophisticated on beta. Maybe you can use an AR1, whatever. But a random walk can be used for description, but cannot be used for forecasting. So, like, I'm wondering, like, you know, what is the advantage of having a time-varying beta relative to, let's say, quantile regression with constant beta? I mean, in terms, you know, for forecasting. Then, my third comment is about the simulation. You have a simulation start, which of course is always nice to see, and you have this kind of setting, okay, where beta follows a random walk, okay, it's highly persistent, and then you have, you know, shocks that, you know, you are sampling from various exotic, you know, quote-unquote distribution, okay? Now, to me, I mean, the simulation study is nice, but it seems a bit disconnected from the rest of the paper. Why? The first reason is because here you have a contemporaneous relationship between y and x, whereas in your empirical analysis you have a predictive relationship, so maybe things can change. And then the second comment would be that if you want to convince me, you need to run also in simulation an out-of-sample exercise, because otherwise you can have overfitting in your simulation study. Then you show, in your table that actually if you compare a simple, standard regression, let's say with quantile regression where tau is equal to 0.5, this is a median, so you show that if you have a Gaussian error, actually the standard model does better, okay? The standard model is very close to the quantile regression if you have kurtotic shocks, even when you have outlier. Now, regarding the skew distribution, I'm surprised that you have a large difference between the mean, okay, the standard model, and your quantile regression. So I was wondering, if you can simulate the data, you can calibrate the shock as if you sample from a skew T distribution where you set the kurtosis and the skew parameters close to the historical data, because I don't know how you have calibrated this shock, okay? And then perhaps you can also add more than 2 regressors, because in the simulation you only have up to 2 regressors. I'd like to know what happens when you have more than 2 regressors, 3, 4, 5. I really want to see, to what extent this methodology is robust to a number of additional features. Now, the comment 4 is regarding the analysis with the actual paper, with the actual data, sorry. So as I said before, you use more than 20 predictors, and then you mix and match with different specification. You typically find that the quantile regression, tends to do better than other specification. But even here, can you provide an out-of-sample assessment? Because, as a financial economist, I'm very much worried about in-sample overfitting. So I really want to see an out-of-sample assessment to convince me that, this is the right path for our future understanding. The second one is you only show results for 1 year and 2 years ahead, but I want to see 1 quarter ahead. This is where you have to show me that your model is better than the simple OLS. Okay? So you don't show the results. I don't know what happens there. And also, there are monthly data. Why don't you use monthly data? Why do you use quarterly data? If I'm an investor, I care about inflation on a month-to-month basis. I don't care about inflation on a quarter-to-quarter data, because I think not only central banks nowadays, but everybody cares about inflation. So I'd like the authors to really broaden up, their paper. And and I think you could also extend the analysis to other countries. You said you want to do the US, but I would suggest to use emerging market economies, because there you can see lots of swings in the distribution of inflation. Okay. Then this is my last comment. Now your inflation modeling by construction is backward looking, because you need to use past data. Okay. But market participants are forward looking. So what can you do here? You can compare your model-based forecast to the distribution that you can imply from the survey of professional forecasters, which you have at ECB, or you can use consensus forecast from consensus economics. Now, you can also implement the model averaging, because ex ante, as of today, moving forward, we don't know which predictor is going to do well. So it would be nice to have a model combination across different predictors, different combination. And then, since I'm a finance person, I'd like to see, the economic evaluation of this exercise. By how much do I improve, okay, if I switch from the naive regression method to the more sophisticated method that you propose. For example, you can work with inflation-linked bonds, and then you can imagine that an investor will allocate his wealth, on these bonds, either using the simple naive model or the more sophisticated model. Then you can calculate the certain equivalent. Because I'd like to see if the gain is 1 basis point, then there's no way, there's no reason for me to switch to this more sophisticated model, because if you read the paper, you realize that it's highly sophisticated. Okay? And to sum up, so if you want to understand how important is modeling inflation risk with quantile regression, well, if this is the question that you have at the back of your mind, this is the paper that you have to read. Okay? It's a very, very interesting paper. I learned a lot, and I look forward to seeing the new version of this paper. Thank you.
Thanks very much for the comments. Very, very grateful that you read carefully the paper and went through every part. And I can tell you that indeed we will, of course, address some of them, like include more motivation and economic intuition and so on. I think that on the simulation I will pass it on to Dimitris. He will go pull his shirts up and then go into work. In some cases, I think it's a very valid, interesting consideration to consider. I mean, extension to consider. Say the time varying parameters. It is typically the case that in empirical you use empirical models, random walk specifications. I can think of also many inflation models, but it's true that if you look at with longer time horizons, maybe also what is happening now. Maybe it could be worthwhile exploring AR1 specification. I think it's very interesting. On the comments on application, I'm not sure I fully understand, because what we showed was the results of an out-of-sample assessment. So all these exercises in the table, the ranking, it's all based on an out-of-sample assessment. So this is what was shown. Admittedly, we had also computed for 1 quarter ahead, 2 years ahead, and several. But for simplicity, instead of showing like 20 tables, or like too many tables, which we just selected some to make the points we wanted to make, which are enough. But we have also, maybe we will add an annex with more results, including 1 quarter ahead. Monthly data, as mentioned, I think we started with the Phillips curve as a reference model. So for economic slack, output gap measures, it's only available at quarterly frequency. You could interpolate, but then you introduce an additional dimension of uncertainty. So we try to avoid that. So then, exactly. Other countries, of course, will be very interesting indeed. And finally, yes, I think it's a very good idea to compare maybe to SPF or other set of expectations, which to some extent we have. We don't have a systematic for every horizon and so on. But, to some extent, we did it already, and sometimes it's more like for HICP as opposed to core. So that's, and of course, it's available for GDP, so that definitely we will consider. And, model averaging, I think we will definitely consider whenever, in the extension I mentioned, where we want to see also, combinations of models, not only, but also variables. And then on the last point, I think it would be definitely interesting to compare how much they can, how much value they can add. And I understand from a financial perspective. And we will, probably take a look and see whether, within models of inflation-linked bonds, if you don't hear from us anymore, it means that it worked, and we are in a private, investment fund trying to exploit the model, right? So, yeah. And the question, so I'm not 100% sure I fully understand, but I can tell you that we have started to apply this model also to headline inflation, because at the end this is what is of interest also for our regular quarterly analysis, which we are sending to the Governing Council. And okay, the results are broadly similar in terms of headline versus core, except that you need a little bit, well, we added more variables also to capture these, especially specific shocks like to oil. In fact, recently we added also variables to capture oils to gas prices and electricity prices, because this has become particularly important. So you have to indeed adapt sometimes the whole infrastructure to the situation, which is becoming more prevalent now and more pressing. So indeed, this is one way to capture specific shocks, which of course it's difficult to anticipate which ones were becoming particularly important. And indeed, even in the COVID periods at the pandemic, then in the extension for inflation, it turns out that at the beginning was problematic, the model, but now that inflation levels are stabilizing again and are not crazy, then the model works nicely without any need for corrections. While for real GDP, where you see GDP in 2020 Q1 spiking, sorry, down fundamentally, then the following year for annual growth rate spiking at a lot. You need some correction, either some outliers or some other corrections indeed to take into account these very specific shocks, which are probably not only unprecedented, may hopefully not appear again, but okay, you need something to take that into account.
So as I said, you can think about this work as an application of the previous ideas to the economy of Israel. So the work is titled Inflation Risk in Israel. This is a joint work together with Osnat Zohar, who is my co-author and also works in the Bank of Israel. Okay. So the motivation for the paper is that tail risks or extreme scenarios may be important. You can see from the quote here that this view is also shared by the Monetary Policy Committee of the Bank of Israel. And motivated by this understanding, we are trying to analyze the entire distribution of inflation in order to look at the tails of the distribution and not just its center. So we basically provide a tool that answers the following question. Given current real and nominal condition, what does the expected or the forecasted distribution of inflation looks like? So here you can see the realized inflation in Israel, and we can notice that its distribution is changing over time. So for example, if you look at such aspects as the average inflation, that would be the green line, and the variance of the distribution, that's the blue line. You can notice that around 2014, both of them seem to decline, and they are lower than their previous levels. So what we do is analyze the forecasted distribution of inflation, and we try to identify the explanatory factors that are associated with those changes. Okay, so my plan for today, I'll introduce to you the methodology. I'll do it briefly since Alberto already done this stuff. I'll talk about the in-sample features of the forecast distribution, and I'll present the explanatory factors that are associated with those features and the changes. Later, I'll talk about the effective lower bound, because that was very relevant for part of our sample. As Pascal correctly noticed, we need to apply an out-of-sample forecast performance if you want to evaluate the performance of the forecasting model. I'll do that in section 4, and then I'll conclude. Okay. So the purpose of this chart is to motivate the use of quantile regression. You can use quantile regression in order to estimate your relationship of interest in different regions or tails of the distribution. So here you can see the relationship between inflation expectations, that's the horizontal axis, and future inflation, that's the vertical axis. And the middle or the median relationship is given by the black line. The red line looks at the left tail of the distribution, a kind of abnormally low scenario, and the green line looks at the right tail of the distribution, the 95th quantile, or in the kind of abnormally high scenario. And the main message of this plot is that it's important to look at the tails, because the relationship at the tails, the green and the red line, can be different or even opposite to what's going around in the middle of the distribution. So this approach of using inflation in order to analyze distribution was introduced by those authors. It seems that we are reading the same literature. Alberto already introduced it, so I'll skip. Before I go into details, I'd like to talk about our main results. When we look at the forecasted distribution, we look at several aspects of it. So for one thing, we are looking at the upside risks. Those are risks of abnormally high inflation, and downside risk. Those are risks of abnormally low inflation. And when we look at the balance of those two types of risks, we find that they were relatively balanced prior to 2014, and then downside risk became more dominant. We also look at forecast uncertainty, and it seemed to decline after 2014. And when we ask ourselves what are the factors that are associated with those changes, we find that inflation environment, that's realized inflation and inflation expectation, plays an important role. Another important factor is oil prices, especially when it comes to forecast uncertainty. Okay, so about the methodology, we use quantile regression in order to estimate this equation. So what we are trying to do is to explain future inflation by 5 explanatory factors. Those are current inflation, long-term inflation expectation, the output gap, and change in oil prices and foreign exchange rate. We do use monthly data, by the way, so it may help for our results. So what you see here is the estimated coefficients of the regressions. You have a panel of 5 plots, one for each of the explanatory variables. So if you look at the upper left panel, you can, in the upper left plot, you can see the relationship between current and future inflation. Each bar represents a corresponding quantile. So the left blue bar represents the left tail of the distribution, the right gray bar represents the right tail of the distribution, and the median is represented by the bar in the middle. And what you can see here is that there is a positive relationship between current and future inflation that just reflects the inertia component in inflation. You can also see that this relationship is relatively stable across the distribution. The bars are of similar size, and they're pretty close to the dashed line, which represents an OLS estimation. Now, if we look at the left lower plot, we can see the relationship between oil prices and future inflation. Again, a positive relationship, but it seems to be more pronounced in the center of the distribution. You can see that the tails are insignificant, and the right tail is of a much smaller magnitude. So an interesting result, perhaps, or a surprising result, is the relationship between the output gap and future inflation. You can see it here on the right upper plot, and we see a negative relationship. We think that a possible explanation is the empirical fact that the output gap is currently correlated with itself in the future. So overheating of the economy today perhaps suggests some cooling down in the future, and that means lower inflation. At least that's our hypothesis. So now I'll talk about the in-sample features of the forecast distribution. First, we can answer it. Sure. The exchange rate? No. You are talking about the lower.
Each bar is the coefficient for that particular quantile.
Correct.
So if I take the 10th decile.
Oh, I see. Yes. You are absolutely correct, and I'll get to that in the forecast. Yes. For this sample, the model is not very good at forecasting abnormally high inflation. Yes, that's a very good point. Okay. So first we can look at the forecasted distribution itself. You can see it here, and similar to the realized inflation that you saw before, it seems that there are changes in those distributions. So for example, around, I don't know how I can point to something here. Oh, okay, that's great. So around this period, you can see that the downside risks, those are the lower gray area, the gray area below the black line, seem to become bigger and more dominant. Next, we are trying to analyze the changes in this distribution in a more analytical way. So we are looking at two aspects. On the left side, you can see the dispersion measured by the interquantile range, and we take it to be a measure of forecast uncertainty. And what you can see is that it fluctuates around some average value until 2014, and then we are starting to see those big drops that represent contraction of the dispersion or decline in forecast uncertainty. So on the right side, you can see the skewness of the distribution. We take it to be the measure of balance of risks. And again, a similar behavior, some fluctuations around average value up to 2014, and then those big drops that reflect the dominance of downside risk. Now here, perhaps I should comment that the data is very noisy, but the main message here is just the change in behavior that you can see here and here. So next, what we attempt to do is to decompose those changes according to our explanatory factors and to see what are the factors that are associated with those changes. When we do that, you can see that the dominant colors are dark and light green. Those stand for realized inflation and inflation expectation. So it seems that inflation environment is an important factor. You can also see shades of purple, especially after 2014, and that stands for oil prices. Okay. Now, similar to other central banks, the Bank of Israel was conducting a relatively accommodative monetary policy. If you look at the policy rate, you can see that around 2015 it's reached its historical minima. We are talking about an absolute level of only 10 basis points. And it seems that in this setting, the effective lower bound issue can be very relevant. it's also important for our story because it can limit the response of monetary policy to abnormally low inflation. So in order to address this issue, we introduce an indicator, dummy variable, that targets this period. We interact this variable with each of our explanatory factors and again try to perform the decomposition. And this is the result of this exercise. So what you can see is that the dominant color is the yellow one, which stands for the ELB period. That means that we cannot rule out that the ELB itself or events that happen in this period are also associated with changes in the distribution. Still, you can see the green color, which suggests that inflation environment is important in this setting too. Okay, so now for the forecasting performance of the model. First, let's look at the out-of-sample forecasting distribution. You can see it here. So the red line is the actual realized values. The black line is the median forecast. And the shaded areas correspond to the areas in the distribution. So for example, the dark shaded area covers 50% of the forecast. And if the forecast is accurate, we would expect the red line to be inside the dark shaded area about half or 50% of the time. So in order to analyze the performance of our model, we compare it to two alternatives. The first one is an intercept-only model. The second one is an intercept and realized inflation model. And we evaluate all of the model by an out-of-sample rolling window. That means that we take some window, estimate the coefficients, and then try to forecast the inflation 1 year ahead. After that, we expand the window by one step and repeat the process. Okay, so in order to evaluate the performance of the model, we need to account for the fact that it provides a range of forecasts. We don't just give 1 point estimate, but rather the whole distribution. So what the evaluation score should do is to take in those range of forecasts, compare it to one realized value, and then evaluate the performance. The first evaluation score that we use is the probability integral transform, the PIT. Its rationale is a ranking one. So for example, if you forecast some low threshold, let's say the 5th quantile, that's a left tail, a very low threshold, for an accurate forecast, we would expect the actual values to be below this threshold in about 5% of the time. From graphical point of view, you want to be as close as possible to the 45-degree black line. And indeed, you can see that the green line, which represents our model, is the closest. It's also the only one who is inside the dashed significant band, meaning statistical significance. Now, the disadvantage of this score is that it doesn't take into account the magnitude of the errors. It doesn't look at the distance between the forecasted and the actual value. So in order to address that, we employ another evaluation score. I saw that Alberto also used it. This is the quantile R squared. You can see that this score does take into account the distance between actual and forecasted value, but that's a relative performance evaluation. What it means is that we are able to evaluate two models. Our model, the inflation at risk model, those are the green bars. And then inflation only or CPI only model, those are the red bars. And they are both evaluated relative to the performance of an intercept only benchmark. So we want to be as high as possible, and negative bars means that the model is underperforming relative to an intercept-only model. And what you can see here is that up to the 75th quantile, the inflation at risk does outperform a CPI-only model. Sometimes they come quite close. The inflation at risk underperforms in the right tail of the distribution, and they are both severely underperforming the intercept-only model. That refers to the comment that you suggested before. So it seems that for this sample, the models are not very good at predicting abnormally high inflation. I remind you that those are the good years where we didn't expect high inflation. That's actually before the pandemic. We later extended, this is an ongoing work, so we later extended the period and got better results. Okay, so to sum up, we saw that the inflation distribution is changing over time. This is correct for both realized and forecasted distribution. When we analyzed forecasting distribution, we saw that the balance of risk has changed. Downside risk became more dominant, and the forecast uncertainty declined. And when we ask ourselves what are the explanatory factors that are associated with those changes, we find the oil prices and inflation environment to be important factors. We also cannot rule out that the ELB or events in this period may have also played a role. That's it. Thank you.
Thank you to the organizer and to the Bank of Israel for inviting me here today. So it's a pleasure and an honor to discuss this paper and be in this session. And before I start, let me remind you that whatever I say now are my views, not necessarily those of the BIS. So this is a nice application of the inflationary risk framework to Israel. So why do we need inflationary risks? I think there are two reasons. One is that focusing on the conditional mean or median or predicted inflation is insufficient for policy making. I don't need to add more to this. And another important reason is that some risk factors may have small or no effect on the conditional mean or the median, but could have a large impact on the tail. So one example is the financial conditions, and this is an key results in a paper by L'Oreal, Lopez Salido, and also our paper at the BIS is that we find that financial conditions have very little impact on the mean, but also a quite significant impact on the tail of the distribution. Now, what are the characteristics of the analysis? Obviously focus only on Israel. Monthly data that cover the inflation targeting period in Israel up to the pandemic. The focus is on the 12-month ahead core inflation, excluding housing costs because I think it's difficult to model them for structural reason. The risk factors are taken from an open economy Phillips curve, so the previous, so Alberto showed the specification used by Lopez Salido and L'Oreal. We use in our analysis BIS a similar specification, quite similar for our analysis of a large sample of advanced and emerging market economies. And there is emphasis on the output sample performance. So what are the main findings? So the author find that from the start of the inflation targeting period, the inflation distribution has remained relatively stable, but starting 2014, the distribution shifted to the left, dispersion decreased, and also the author also find that downside risk to inflation also increased relative to upside risk, so the skew is to the downside. And what has driven this change are falling inflation, the falling oil prices, and potentially also the effective lower bound. I think that there is some evidence for this, but it's not conclusive in your paper. And then the author find that not all models perform well, but the unrestricted model performs better, and no model capture the upside risk well. So I have three main comments. So my first comment is that the main findings of the paper are in line with those that we find for the analysis of the emerging markets. So we use a panel data with a large number of emerging markets. My second comment is that there may be, okay, this is a question for the authors, whether there is a way to improve the specification of the model, although the sample is not that big. And I would make three comments, one on the output gap, financial condition, the role of exchange rate and fiscal policy, and finally, I have a comment also on how to present the results. So, main finding. So basically, the results of the paper are largely consistent with what we find for a panel emerging market. In particular, we find that inflation and also the short-term inflation expectations have a large impact on the upside inflation risk. So what we find is that there is a non-linear relationship of the coefficient on inflation or inflation expectation across quantiles, and this relationship is monotone, so it is very low for downside risk, and then it increases up to the upper quantile. So which means that when inflation falls, the distribution narrows, dispersion decreases, and also the upside risk declines. So the right tail of the distribution moves more than the left tail of the distribution. So you have the distribution become more skewed to the downside. We also found that the effective lower bound is a quite significant driver of downside inflation risk, move the left tail of the distribution in the sample of advanced economies. Unfortunately, we don't find the same results in the sample of emerging market. We don't have enough observation for this. And finally, we find that inflation targeting reduces median inflation, but also has a larger effect on upside and downside risks. And this effect is quite significant in the sample. It's quite big in the sample of emerging market, much bigger than in the sample of the advanced economy. So the authors cannot look at this because they have only, their sample only covered the inflation targeting period, but this is something to keep in mind. Now, on the model specifications, I think the output gap has the wrong sign, so obviously this is a bit problematic. So the obvious question here is whether you have a better measure of the output gap. So my understanding is that you are using a composite indicator of economic activity, which you estimate, which is the unobserved component in a model where, in a time serial model where you have manufacturing, production, employment, sales, you have import and exports, I think. And it's a model that also has some region switching, in the sense that the coefficient changes when you have expansion or when you have a recession. So the question, obvious question here is whether this is really a good measure of cost pressure, of slack in the economy. And I mean, the theoretical, I mean, if you look at the theory, the appropriate measure is the real marginal cost, and this is not observable, but can be approximated with the output gap. Not necessarily, depends on the, depends on properties of the economy. But the obvious question here is whether you could find other measures, the monthly frequency that you can test in the model, like unit labor cost, unemployment rates, or the trend that industrial production, etc. Also, another question is whether the HP filter that you use to calculate this, to detrend your measure of economic activity is too smooth. So I don't see how you have this estimate based on a region switching model, so I'm not sure that detrending it with the HP filter is the right way necessary. And also there might be also some structural changes that I'm not aware of in the Israeli economy that might make the HP filter inappropriate. Okay, so the other things that I am a bit surprised is that you haven't, I don't know if you have looked at this, but this is obvious question is whether you also tried a measure of financial conditions, because we know from the paper from Lopez Salido and Loria, also from our paper, we find that financial condition is quite an important variable. So in the case of Lopez Salido and Loria, the financial condition affect the left tail of the distribution. In our analysis, in emerging market, financial condition affect both the left and the right tail of the distribution. So it increases increase the dispersion of the distribution. I mean, one reason why financial condition, tightening the financial condition in emerging market affect also the right tail is that this is often associated with the exchange rate depreciation, a tightening of financial condition, and this drives also inflations up. So here I plotted a couple of measures of financial condition. One is a Goldman Sachs financial condition index. The other one is a real-eye equity return volatility. So there's something going on. I mean, this is an easing financial condition, and this is a tightening, and it actually seems to track your, the dispersion of your, the measure of your dispersion, if you use the Goldman Sachs measure. So there may be something going on there. So So it would be interesting to know, if you try this variable. Other thing is surprised me is that the exchange rate is not statistically significant. Now, based on our analysis on emerging markets, this is one of the most important factors driving inflation risk in emerging market. Using different measure of the exchange rates. Now, question. So here I'm plotting the bilateral US dollar exchange, the effective, nominal effective exchange rates. Now the question is, what is the relevant measure of exchange rate in your model? So US dollar might be relevant for financial conditions, but for explaining inflation, maybe the euro might be more important. I don't know exactly, but a measure of the nominal effective exchange rate. And here you also have, the US dollar and nominal exchange rates track each other from 2004 relatively well. Then there is something going on here. So I don't know if that might be relevant for your model. Now, given that you don't find a significant role for the exchange rates, I asked myself, what, is there a good reason why? So there could be a couple of possible explanations. One is the monetary policy regime. So, you have a strong, credible inflation targeting regime. The second is that despite the fact that public debt is relatively high, you don't seem to have in Israel significant external vulnerability in terms of how this debt is financed. So I try also to compare this, this you're finding also with the paper that we'll present tomorrow, which is on the fiscal sources of inflation risk in emerging market developing economy. So here we find that one other question is whether also you look at the fiscal variable. So what we find here is that the change in the fiscal deficit has a strong impact on exchange rate in emerging markets. And the effect works also through currency depreciation. We also find that the way that debt is financed is relevant. So if you have large foreign currency debt, if you have a large share of foreign investor participation in local debt market, this is associated with a larger currency depreciation. And we also find that in inflation targeting emerging market, the effect on the exchange rate is much attenuated. It's almost eliminated. So given that, here we can see that in Israel, foreign currency debt is like 15% of the debt. Participation is like 10%. So this is well below the median of emerging markets. So, and you also have an inflation targeting regime now. So it could be that the exchange rate is not really important in Israel, but that's something that is something for you to consider more carefully. And also on the top left, this is the overall, in the primary balance. So there is significant variation in it. I don't know if you try to see that is relevant. And starting from 2014 onwards, the difference between the two lines, which is the interest payment, is declining, and we find in our analysis that this is one predictor for inflation and inflation risk in the full sample of emerging markets. So now, okay, so that's my last comment. So you present the composition of the summary statistic, the dispersion and the skew. My suggestion would be to show how the forecast change from one period to another, and also to look at what variables are driving this change in the forecast. So this is an example that I computed using the panel coefficient estimates from our model, so that the estimates are common across the country, so they might not be appropriate for Israel, but this is what we get. And so clearly you see from end of 2013 to to 2015, clearly distribution shifted to the left. Here it's not measured, but it's not clearly visible, the dispersion decline and the upside risk decline as well. And here, these are the contribution to the changes, to the various quantiles. So we find here that inflation is the main driver. But we also find, if you look at the red bar, is the equity return volatility. This is a proxy for financial condition. And we find that there is some dispersion here, that the volatility also matter increases the dispersion of the forecast distribution. So to sum up, this is a nice, careful implementation of the inflationary risk framework to Israel. My main comment, question is whether you can still improve the model, especially with a better measure of the output gap. And finally, I think you should try to complement your analysis of the driver of dispersion and skew with the drivers of the changes in the forecast distribution.
Hello everyone. It's a great pleasure to be included in this session, and I'm going to be talking about debt inflation. In particular, I will focus on corporate debt, how it could hamper the efficacy of raising monetary policy rate in terms of controlling inflation. And this is joint work with Charles Goodhart, Dimitrios, Tsomocos, Udara, Peiris. My name is Xuan Wang. I'm at Vrije, Amsterdam and Tinbergen Institute. The rise of public debt has received much attention recently, but it's fair to say that the rise of corporate debt, by that I mean non-financial corporate debt, has received relatively less attention. In this paper, we argue these high levels of corporate debt may actually impede the transmission mechanism of monetary policy, and therefore make it less effective in terms of controlling inflation. And this is because the distributional income effect of higher nominal interest rate can offset or even dominate the usual negative substitution effect on aggregate demand, and it is quantitatively important. And we show this mechanism is independent of standard financial and nominal frictions, and instead works through the heterogeneous households and reinforces the working capital channel of monetary policy. And I'll be more precise as I unpack the model. Just a few numbers and stylus facts to put things into context. This table displays the non-financial corporate debt as a percentage of GDP across advanced economies and emerging economies. And we can see that corporate indebtedness has been on the rise ever since the global financial crisis, and even more so since the pandemic crisis. And if I can draw your attention to the graph on the right-hand side here, we can see that more recently there is a dramatic surge in terms of corporate indebtedness, illustrated by the red solid line here, and also the surge in inflation, core inflation, illustrated by the blue dash line. So it is interesting and relevant to ask, given the high levels of corporate debt in the economy, to what extent is raising short-term interest rate effective in terms of controlling inflation? And that is the key question for our exercise. So our paper connects with the flourishing literature of corporate indebtedness and the macroeconomy, in particular on monetary policy transmission mechanism. Much of the existing work tends to focus on the drag of debt on real investment, or the impact of unexpected inflation, how that changes the real burden of debt, but less attention has been paid to how corporate indebtedness could be a source of inflation and make the efficacy of monetary policy in terms of controlling inflation less effective. And that's how we see our work fitting into the literature. Our paper is going to make use of a two-agent heterogeneous agent model. So in that sense, it connects with the heterogeneous agent Neo-Keynesian framework. And as you shall see, the income effect through corporate debt is going to reinforce the working capital channel of monetary policy. In the interest of time, I won't be able to do full justice to the set of papers here. For the rest of the presentation, I will first give you a very simple stylus model to obtain closed form solutions and deliver the intuition and then we embed the simple model in the dynamic New Keynesian model to study the shock propagations. So for the simple model, the economy has two households, an owner household and a lender working household. So the lender working household, they hold safe corporate bonds and supply labor, and the owner households own firms that issue corporate bonds for financing. So we can think of the owner households as the top rich, extremely rich people in the economy holding a lot of shares in their stockfolio. Think of Bill Gates and people like that. Top 10% income group. Whereas the lender working households, they supply labor, they hold a lot of fixed income securities in their portfolio. And this is consistent with the vicious narrative of the economy consisting of an enterprise borrower and a creditor, the salaried man or the laborer. Recently, there's also empirical evidence on the top rich investing more in stocks, whereas the lower income group or middle class investing more on liquid safe assets. Lender working households, like I said, they supply labor and they do not actively participate in the equity markets. The firms are subject to working capital financing constraints, and this is where money enters the economy against an offsetting bank credit to finance the working capital along the lines of Barth and Rami, Cristiano, Rovina, and Walsh. For the older households, they are the ones that hold a lot of shares in their portfolio. They have a simple utility function. In the dynamic model, we're going to have very conventional utility function, but here is to derive analytic solutions. They derive utility from output. They have the firm's profits in their resources. You can think of that as the dividends from the firms. Moreover, they start off with some outside money or monetary endowment in their pocket, which is denoted as M. M is exogenous here for now, and that can be as small as it can be, a positive epsilon. And this in the literature is referred to as seigniorage transfer, used to determine the price level in equilibrium. We're going to endogenize that in the dynamic section through central bank's discount window and open market operation. And they consume the real output. In terms of the lender working households, they also derive utility from consumption, and they suffer this utility from labor. In the morning, they work, they obtain the labor income and carry their monetary proceeds, their wages, until the evening. In the evening, they have their labor wages, but moreover, they hold corporate bonds as assets. They receive the repayment from their corporate bonds as part of their monetary proceeds, denominated in these terms. The D is the level of legacy, corporate legacy debt. The R is the corporate bond rate, the gross interest rate, and the psi is the fraction of the corporate debt repaid. And all of these terms are taken exogenous and will be endogenized later on. For the firms are owned by their owner households. It's very simple production function. In the morning, they haven't sold their proceeds, so that's why they need to apply for working capital credit to borrow money to pay for the wages, because they haven't received their revenue. They got the working capital and the money to pay for the wages. In the evening, they sell their output and use that monetary proceeds or the revenue to first of all pay back the working capital credit subject to the borrowing cost in the money market, and that cost, interest rate I, is the monetary policy rate. Moreover, they pay the fraction of the corporate bond that needing to repay in that period to the lender working households. What's left over is the nominal profits. Okay. Equilibrium is defined as an allocation of resources, and given positive prices and positive interest rates, monetary endowment and corporate legacy debt, such that the firm set prices while taking into account the price impact on the demand. So there's a markup between product price and wages. Agents maximize subject to the budget constraints and liquidity constraints. Goods market, labor market, in particular, money market also clears, so we can obtain analytic solutions as well as output. This lemma helps to characterize the equilibrium. First of all, we show that contractionary monetary policy unambiguously reduces real wages. So real wage is an expression of technology, markup, and the monetary policy rate. And more interestingly, we derive the labor supply elasticity as an expression of corporate debt and working capital. Working capital is a short-term credit for working capital financing, and that's obtained through the money market. And corporate debt is of a longer term, and that's held by the lender working households. What we show here is that the labor supply elasticity increases on the real value of corporate debt and decreases on the real value of working capital. And this is interesting because labor supply elasticity not only depends on the preferences, but also it depends on the household's portfolio, the debt condition in the economy. And that's consistent with empirics in Ziliak and Knisler and Cesarini and so on. So with the lemma, we can derive the aggregate supply curve and the aggregate demand curve of the economy. And that is to say, we first do not let the goods market clear yet. We let the labor market clear and the money market clear, and then we derive the relationship between price level and output. In terms of aggregate supply, we can see the debt condition affects the curvature of the aggregate supply curve. And also, the debt position enters the aggregate demand as well. In particular, if we look at the aggregate demand, when we raise the interest rate, the monetary policy rate, usually it increases the financing cost of labor and less is demanded. And that's why raising interest rate has a dampening effect on aggregate demand. On the other hand, the presence of legacy debt gives an upward pressure on the aggregate demand curve. And this is because when you raise interest rate, the presence of debt renders labor supply more elastic, as we have seen in the previous lemma, so that the increase of I causes the decrease of real wage expenditure to offset the increase of the financing cost. So what's the intuition? The intuition is the income effect of corporate debt affects both the AS and the AD. On aggregate demand, after monetary contraction, we have the usual downward pressure on aggregate demand through the intertemporal substitution effect. Moreover, with the high fixed cost of debt, the firms feel the need to spread the fixed cost over a larger production cycle, production scale, and demand more labor, and that leads to an upward pressure on aggregate demand, and that's the income effect through the demand side, or the general equilibrium effect, if you will. On the AS curve, after the monetary contraction, the negative impact on the lender working household's wealth is less in the high debt scenario than in the low debt scenario. So labor is more elastic when the corporate debt is high. The lender working household hold a lot of corporate debt in their portfolio after monetary contraction. Even though their real wages goes down, they might as well just sit back and not work as much as the scenario when they don't have a lot of fixed income securities in their portfolio. Interestingly, when we change the model into a representative agent framework, we see that the income effect of debt disappears in the aggregate demand. And this is because in the representative agent case, the distribution of income doesn't matter because one is lending and borrowing amongst themselves. So that is why the debt only matters in this framework once we decentralize the economy and make it a two-agent or heterogeneous agent framework. In terms of analytics in equilibrium, we show the following. When the legacy debt, corporate legacy debt is sufficiently low, and that is this condition holds, the standard Taylor principle applies that raising policy rate lowers inflation. However, the higher the corporate legacy debt is, the lower the drop in price level or inflation is. And that is to say, the presence of debt makes raising interest rate less effective in controlling inflation. There's also an extreme scenario, and that is to say the amount of repayment of corporate debt times the policy rate is larger than the working capital. The Taylor principle is inverted. Raising monetary policy rate can raise inflation. However, this scenario is unlikely to hold in reality, because in reality, the parameter psi, the fraction of corporate debt to be paid every period, is extremely low. So this is unlikely to hold, and in our data calibration with a dynamic model, possibility 2 is also ruled out. So we focus on the first possibility when the Taylor principle applies, but the presence of debt makes controlling inflation trickier. Graphically, let me show you what's going on here. If we can just look at the left-hand side, I'm plotting the AS and AD curve that we derived from the simple model. Horizontal axis is output, vertical axis is price level. The original equilibrium E is here. After the monetary contraction, AD curve moves to the left, and the AS curve in the low debt scenario is quite inelastic. It also moves a bit. So after monetary contraction, we can see a lot of action in terms of the drop in inflation and price level, and also output drops. Now, let's move to a high debt scenario. When the corporate debt is high, as I have just shown you, the AS curve, due to more elastic labor supply, becomes flatter, and the AD curve, after monetary contraction, also moves to the left. But because of the income effect through debt, there's an upward pressure on AD, so that's why the action in AD curve is smaller than in the low debt scenario. All in all, in the high debt scenario, although we can see a lot of action from allocation, see the output drops, we don't see much action in terms of the decrease in price level or inflation. The presence of debt, that's income effect, makes raising interest rate less effective in pushing down prices. So taking stock, so far we have assumed that no firms expected to go into bankruptcy. This is because policies were expansionary until very recently, and amid the pandemic crisis, given a lot of support, the number of firm default was very low. However, if we were going to consider bankruptcy possibilities, the basic problem or the conundrum facing monetary authority is a small increase in the short-term interest rate might not be able to restore inflation. However, a larger increase in the short-term interest rate might bring about bankruptcy, leading to a recession. For the rest of the presentation, we study the quantitative importance and show the mechanism of the static model also holds in the canonical New Keynesian framework. So we're going to move away from the flexible price equilibrium by considering sticky prices a la Calvo pricing. We're going to have an endogenized monetary policy rule. In the dynamic model, the wholesale producers are price takers. They access short-term financing from the money market to finance their working capital, and they also hold longer-term corporate debt to the lender working households. Intermediate goods producers are static price setters with market power, and that's standard with the literature. We assume that the steady-state level of corporate legacy debt, which the wholesale firms choose to roll over at prevailing interest rates. They will also replace the exogenous monetary endowment of the households with central bank open market operations in the bond market. Skipping each agent's maximization problem, I'm just going to highlight the Phillips curve and the dynamic IS curve, how it is augmented via the debt mechanism. So the Phillips curve is a structural relationship between inflation and the marginal cost. And we show the marginal cost in this framework is going to be affected by the price of the corporate debt as well as the quantity of the corporate debt. As the steady-state level of corporate legacy debt increases, the absolute value of the coefficient on the interest rate on the path of inflation declines, and that means changes in interest rate or short-term interest rate have a smaller negative effect on inflation. How about the dynamic IS curve? The dynamic IS curve is also affected by the level of debt as well as the price of debt. The level and dynamics of corporate debt affects both affects the aggregate demand through the marginal cost. And the output gap in this framework reflects two distortions. One is price rigidity, and second is market incompleteness affecting the wealth distribution among the agents. Putting some numbers into the dynamic model, we conduct some quantitative examples and policy experiments. What we do is that we take the standard calibrated parameters from the recent literature. In particular, the Taylor rule responds to inflation 1.5, smoothing parameter is taken as 0.5, and in our benchmark model, the output coefficient is set to 0.2. Now, we take a benchmark corporate debt GDP ratio at a steady state at 75%, and a high debt scenario as 100%, compared with the recent scenario that 100% is still a very conservative take. So what we have here is that, first of all, as the debt level increases, we show the more pro-cyclical owner households consumption appears, and more acyclical lender households consumption becomes, connecting to the household finance literature. More interestingly, we conduct a monetary policy experiment whereby we consider two types of central bank reaction function. One is a central bank that is very hawkish on controlling inflation, and by that you can see that's illustrated by the red solid impulse response functions in response to a contractionary monetary policy shock. And in this hawkish central bank's response function, the output coefficient is 0.2, but the central bank is very responsive in terms of controlling inflation. We also consider a relatively dovish central banker, and that response is illustrated by the black dashed line impulse response functions. In this reaction function, the Taylor rule has an output coefficient of 0.9, and that was taken from Janet Yellen and Ben Bernanke's speech after the global financial crisis. As we could see, if the central bank is very hawkish in terms of controlling inflation, it could do so. However, the loss of output is much bigger and more persistent. However, if the central bank attaches more weight in the Taylor rule with the output coefficient of 0.9, inflation is going to be very high in the short term, whereas output could go back to the steady state more quickly. So this underscores a much acuter trade-off between inflation and output stabilization, and it reinforces the cost channel of monetary policy. Now, in terms of the robustness check, we also consider a fixed coupon bond for the corporate debt, and all the results go through. In the interest of time, I won't be able to go through the specifics, but this is something to do with the term structure with the interest rate and the flattening of the Phillips curve. And if we have time, we can discuss on the robustness check later on. So to sum up, in this paper, we developed a general equilibrium model with money to study the effect of corporate indebtedness to monetary transmission mechanism that we show the working capital as well as the corporate indebtedness affects the shape of the Phillips curve, pretty much connecting quite well with Alberto's presentation just now. Higher level of corporate debt level render contractionary monetary policy less effective in terms of controlling inflation. When the level of corporate debt is sufficiently high, contractionary monetary policy may even raise inflation, although with parameterization, that's an unlikely scenario. So the mechanism of a central result is via income effect through debt, and future direction, of course, would be interesting to search for the threshold of the rise in interest rate such that the debt deflation equilibrium could occur when we consider the possibility of bankruptcy. The possibility of bankruptcy is what we have assumed away so far. So we'll focus on debt inflation. Thank you very much, and I look forward to Federico's discussion.
So thanks to the Bank of Israel for organizing this great session of us central bankers concerned about inflation. So this is a paper that has a lot of potential to go in many different directions, and I think the authors will be able to get 2 more papers out of this framework that they have come up with. So let me say first of all that we have here a model in this cost channel literature where we find we look for a simple way to introduce financing constraints. Essentially, that's what this family of models, so-called cost channel models, are set up to build. And the reason why they are simple is because the question is about a trade-off for the monetary policy maker and possibly building a second-order approximation of welfare functions. So it's something where we want to build some narratives. They're not necessarily quantitative models that we want to use to forecast inflation. And they're all they're called cost channel models because they're born from the so-called Wright-Patman effect. So this Congressman Patman, congressman from Texas, was claiming, well, high interest rates are causing inflation. And of course he was wrong, but the idea was, I'm a car dealer, I have all these cars on the lot, I borrowed a lot of money to keep this inventory, and this is my working capital. And if you raise the interest rate, you're raising the cost for me of keeping all the cars on the lot, the huge inventory, and they're going to have to raise prices. So that's the idea which makes sense, not really. Patman was not a great economist. So the traditional position that monetary economics has had is that, maybe this is true, but we believe that in the long run, if you raise interest rates, if you raise real rates, this is going to be a contractionary policy and will lower inflation. At some point, this will happen. This is what we believe, and this is what central banks believe. But what the cost channel models point out is that this could be very much attenuated. It could be that there's a much worse trade-off than we think, because there's this cost, this working capital cost channel way of transmitting monetary policy. So when I raise interest rates, in the long run, I'm squeezing demand and I'm lowering markups and lowering inflation. But in the short run, I'm also increasing the cost of keeping all this inventory. So this could be, this would lead to having a worse trade-off. So the question that I had in my mind was, okay, so we know that the cost channel will attenuate the power of monetary policy. Now we have 2 financing constraints in this model because we have working capital, so you can call it short-term, I'm financing wages, and then you have corporate debt, which is more in our mind equivalent to long-term, so I'm financing capital investments. And this is the way in which the model works. So what do I get out of having 2 financing constraints instead of having only one? So we know that we will get some attenuation results, but what else do I get? So since I know that we have lunch coming, so I'll go straight to the 4. Instead of the usual 3, I came up with 4 comments. So the one result is changing the interest rate is irrelevant for the steady state level of output if the level of corporate debt is 0. This is one of the results that comes out of the model. So that I should, unless I have corporate debt, then the cost channel is not affecting the steady state. And remember that the steady state is also corresponds to the flexible price level of output. And my answer is no, that is not really true. So it's not something that comes only out of this model. So suppose that you have, this is flexible level of output. If you take away the T, this is also the steady state level of output. And it will depend on all the variables that you imagine. So C is the level of demand shock, A is the level of productivity shock, Chi is some elasticity of labor supply, the capital phi is the steady state markup, and then you will find that there's also the nominal gross risk-free interest rate. And why it doesn't show up in the model in the paper is because they use log utility. It seems from the math I did, maybe I'm wrong, but from my math, it's a borderline result. If you don't use log utility, then you will get that the interest rate matters, even if you don't have corporate debt, even if you just have the standard working capital. So this is not the result exclusive to this model. But it introduces a very interesting complication that if I have in the flexible price equilibrium the nominal interest rate, that means the monetary policy that I have in the flexible price world, where I look at potential output. So now when I think about output gaps, I have to think about, well, what's the monetary policy in the efficient, in the first best? And if I only have the working capital, it's very easy, because you want to set the interest rate to zero. But now you have two financing constraints. So that's not true anymore. Now you have a trade-off also in the flexible price equilibrium between one financing constraint and the other. So now you've got to think really hard about, well, what is my benchmark, my potential output? How do I define it? Because it's not straightforward. Okay, so that's one. Then here is the second question. The level of corporate debt is the only financial asset relevant for steady state output. So before the question was whether the interest rate that I pay on working capital matters. And here we're saying, well, is the level of working capital relevant, or it's only the level of corporate debt? And we saw that here I didn't have any level of working capital, but the reason is that the working capital here is set at 1. The whole wage bill needs to be financed. But the answer here is also no, because you can decide to finance just a share of the of the wage bill, and that share I call it alpha. Then if you introduce this alpha, then the quantity of the working capital will enter into the steady state level of output. So it's here. And the lower is alpha, the higher is the steady state level of output. In the same way that the lower is corporate debt, the higher is the steady. So this also is not a feature that is unique to having this corporate debt. You would also get if you only had the working capital channel. Then we go to the dynamic model, and we also ask the question, the dynamic question, well, is the level of corporate debt, very high corporate debt, going to reduce the power of high interest rate in reducing inflation? And so that's also true for the working capital, because now that alpha, you find it in the New Keynesian-Phillips curve right there. So that alpha tells you what is the share of the increase in the interest rate that will end up pushing up real marginal cost, and so fight the monetary authority when it's trying to lower inflation. And by the way, you can estimate this coefficient. It's been estimated. So also for the working capital, as for the corporate debt, you have this issue that how much working capital you have will affect the trade-off or the power of the monetary authority in fighting inflation. And then I have a comment on the quantitative results. So the Wright-Patman effect, if you remember, was, well, maybe I see interest rate pushing up inflation in the short run, but then overall I should see a decrease in inflation. When I look at the impact of a contractionary monetary policy, so an exogenous raise in the nominal interest rate, what we get is this picture where inflation goes down initially and then is positive. And my reading of this plot is that if I plot the price level, you would end up at a higher price level than where you started with. Because inflation is positive for 20 periods, and it is significant. It starts from 0.5%. So it's very interesting that the level of debt affects the size of the response of output. However, we do get a model where contraction in monetary policy is pushing the price level at a higher level than where you started from. And this can happen in these models. It's a very legitimate concern. And it depends on this trade-off between how much you have this cost channel working and how much you have the traditional channels, aggregate demand channels working for monetary policy. And it depends, in my experience, on the parameterization that you use. And there are some parameterization where you will not get an equilibrium at all because this inflation will be explosive. So when we think about what parameters to use, we should think about, well, do I get something where monetary policy overall acts in the way that we are trained to think it should act? So when we think about where to go next and where this model has a lot of potential, is to think about, well, what's the difference between having a lot of corporate debt or having very high level of working capital, revolving credit, short-term debt to finance inventories, for example, or liquidity borrowing. The US would be commercial paper. And there can be a lot that we can gain in terms of insights because there's a big difference in the creditors that you have. You know, revolving credit will typically be a bank in Europe or for everything but the biggest corporations in the US. The maturity, of course, default rate, the risk of rollover, and also firms could have access to different types of credit depending on more long-term corporate debt or more working capital liquidity, depending on their age and depending on their size. So you could get a lot of very interesting considerations. For example, across countries, it could be that you have countries with a different distribution of firms' age, and they get financed in different ways. So the share of corporate debt long-term to working capital is very different. There's also a very interesting consideration that is motivating the paper. That is, we are very worried about sovereign debt, but not so much about corporate debt. And that's an excellent observation. So cross-country, there's also very different implications of legacy sovereign debt. For example, Italy. So sovereign debt is this blue bar. So you would think that Italy has a lot of debt, but France has much more debt. France is up here because they have less sovereign debt, but a lot of private debt of non-financial corporates. So when I think about I raise interest rates, I'm making it more difficult to finance public expenditures, maybe, yeah, well, you have to think about these two countries. And if I'm in Italy, I'm making it harder for the treasury. If I'm in France, I'm making it harder for corporations. And we need a model like the one that Xuan is proposing, where you can look exactly at these questions. And inside here, inside this green bar, there could be also different distribution between the working capital and long-term debt. So that's really a great unexplored directions in which the authors are going. So that's all for me.
First of all, thank you so much, Federico, for this very helpful discussion and a lot of food for thought. Just a quick response to the question on the optimal, the working capital interest rate, and how that in the steady state doesn't change the output. It is not a generalizable result there. In general, with this working capital in advance constraint, then when you change the working capital interest rate, the steady state output changes. And in this model, my sense is I have to get back to the derivations more carefully. But my sense is that it's not to do with the log utility, but how we redistribute the seigniorage profits back into the economy through the open market operation. But I need to check on that. Through my past project working on this, so that changing the working capital interest rate does not change steady state output. It's not a generalizable outcome. Usually it does change the steady state outputs, that money is not neutral even with flexible prices. That comes to the second point, that what is the potential output or the natural output in this type of framework, and going back to your question on optimal policy. And that's a tricky one because the optimal policy, as Federico pointed out, when we specifically think of the policy instrument as a short-term interest rate, is just to set it to zero, the Friedman's rule, especially when we don't have default as financial frictions. And when you set that intra-period working capital interest rate to zero, on the output, then you get the first best. However, the problem with that is that we were going to lose price level determinacy. We can get inflation determinacy through sticky prices on the dynamic part, but in the steady state, we can't obtain the price level determinacy. And that's why the only way I can think of in this framework to pin down an optimal policy is not so much through an efficiency point of view, excluding corporate bonds, but it's through a distributional point of view, because we have two households in the economy, borrower and lender. Then pushing the interest rate too low, in the extreme, the price level is going to be approaching infinity, and that's going to have distributional income on these two groups of people in the economy. So I suppose one way to go about what would be the sensible level of short-term policy rate is to look at the distributional income of setting the short-term interest rate. Now, on the policy implications, in the robustness check I didn't show you is that there is a flattening of the term structure of the interest rate. So the reason why the inflation effect on inflation is low is because the labor supply elasticity is big. So if we want inflation to respond, then one way to think about it is to decrease the labor supply elasticity. So when the real wages drop, then people will be incentivized to work a lot. Then to achieve that is just to increase the yield on the long end of the yield curve rather than the short end. Here, we're just raising the short-term interest rate so the yield curve can get flattened or even inverse, and that's not helpful. But through quantitative tightening, by selling bonds at the long end, our conjecture is it might make the labor supply once more inelastic again, so more actions on the prices. But that's something that's a conjecture stage. We haven't incorporated into the model. On the question about the corporate debt maturity, I think that's a very interesting area to explore. I tend to think the effect will be a bit stronger because you have maybe stronger income effect, but we haven't put it down in the model. So I can't say for sure. There's a lot of parameters in the model as well. And that is also an area that Federico thinks that we can explore. But thank you so much for your questions, especially to your comments. I appreciate it.